In this short video, I want to talk through some of the terminology we use in talking about functional programming. So let's get started. We talk about functions, and I explained what a function was in the previous video. We talk about that function taking inputs and giving outputs. And in that case, we think of those inputs and outputs as values. And these are things like numbers, or they might be, we'll find out later, booleans or strings, or much more complicated composite data types, even functions, for example. But they're each of them values. So they're something which represents a quantity out there in the real world in some sense or another. And functions are the things that transform one or more input values into an output value. And then a function definition is an equation that describes the output in terms of the input. So if you remember, we had the equation double of x equals 2 times x, and there in that case x was this unknown input value, and we describe the output 2 times x in terms of the input x. So these things that we call variables or unknowns are written just as they are in mathematics, is by letters, the letters we're familiar with in algebra. And evaluation was the process of running a functional programming, taking a large, complicated expression and reducing that to a value. And that's the result, the output of that program. Now, a crucial thing to understand, and this is a difference with traditional languages like C or C++, like Java and so on, the variables in a functional programming language don't vary. So a variable in definition like double of x equals 2 times x, x stands for any unknown value. It's saying double of something is 2 times something. And that's it. The something is just, it's not defined, but it could be any number. And it's the sort of thing we're familiar with in algebra, things we learnt in maths, and these are exactly the way we think about variables here. A crucial thing is, it's a definition is an equation. It says double of x is equal to 2 times x. It's quite unlike the equals you see in a language like C, which says make the thing on the left equal to the thing on the right by potentially changing the state, changing the values of variables. A functional program has no state. Variables just stand for an arbitrary value, but there is no, it's crucial to understand that a functional program doesn't evaluate by changing values of things in storage locations. Variables are not storage locations. A function simply takes some inputs related, based on those inputs, calculates an output. So you might ask the question, people often ask this question, how can it be sensible to remove features like assignment, variables that you can update? How can removing features make a language better? And the answer is removing features can make some things clearer. So for example, we've said that a definition is an equation. Just as we can in algebra use equations to prove other equations, we can think about proving that programs behave in a particular way by taking the equations that define functions and then using those equations to infer, to deduce properties of overall programs. And that model of where functions don't change a state, they simply turn inputs into outputs, they take inputs and give outputs. That makes it much easier to, I think, to understand the programs and similarly to prove them correct. And because we don't have an assignment going on, it can be easier to combine program parts. And also it can be easier to parallelize the fact that when we're doing evaluation, we're not changing the underlying state of the language, the underlying state of the program, means that if we choose to evaluate in one order or another order or in parallel, the overall result that we produce can be the same, will be the same, because the order in which we evaluate things isn't significant, because we're not changing values of a state, we're simply calculating outputs that depend on inputs. So I've talked a bit about terminology here, but also talked about some of the benefits of this calculational model that allows us to infer things more easily, read programs, makes them more understandable, and combine them and evaluate them in more in a number of different ways, making sure that the results, however we evaluate them, will be the same. So we get advantages from this distinctive approach, and we will come back later on to talk about the idea of immutability. So building complicated data which cannot be modified as a key to writing robust programs in languages with state. So adding immutable data to a language like Java can allow you to program concurrently in Java much more effectively. But that's for a later video.